computer? Yes. All right, and I'm not muted. Okay, so a few things before I start the lecture so everybody gets here. I'm almost done with the exam. I have like 2 more to grade, and then I have to put all the grades on Carmen because I'm doing per question. So overall, it was good. So a lot better than exam 1, so that's good. I will post the solution by Wednesday. And so that's about exam. I reviewed the surveys, the anonymous survey before spring break. I mean, I actually reviewed it, but I didn't want to talk about it before exam. Just want to talk about it after exam. Couple of things that was noted. One is to switch between the lecture and MATLAB. It's not the easiest for some of you to follow. I'm doing my best. This usually is where we need a computer lab, so you can actually use MATLAB on the computer, so you can go with me. We don't have that, but I try to give you the slide at least beforehand, so you can look over, see what's coming in. Or afterward, when you're reviewing lecture, if there's MATLAB, you put MATLAB in front of you and try to put those commands and try to see if you get what I got. If not, then I will expect you to ask questions. All right, so this is the best way to do it. I guess is the best way to do it because I'm also recording, so I have to switch between screens. So it would be on your Zoom because Zoom is not smart enough to follow the screen changes. So I try to do better, but I'm trying to think about many things at the same time. So if you have questions about those, you have to always ask. You don't even have to come to office hours. Send me an email. Hey, Dr. Z, can you talk about that MATLAB slide again, that command? We didn't understand it, okay? Because I think the MATLAB part of this course is really important. It cannot show up in the exam because you don't have a computer, so I can't question you. It usually shows up in your homeworks. You have plenty of time for homeworks to figure those out. So far, all the homework showed that you're good on MATLAB part, but since there was more than one comment about MATLAB switching between lecture and MATLAB, I thought I'd talk about it. I'll try to be better. All right. Some of you talked about class participation. You appreciated, and I appreciate that you told me. So my goal is to always have it. I know, like during the class or right after, it's a little bit pressure, but sometimes that pressure, like the kind of question I ask, is usually very quick. There's just like 5 minutes, 10 minutes if you paid attention. Just to tell you that, hey, did you get this or not? I started giving you more time on those, if you notice, at some point in the middle of the semester. So now they're usually either the next day, like the next class, or at least at the end of the day. So, but the goal is for you to see how much in the class you listen and how much of those you understood. Because even if you are here 100% present, something that I say might not fall into your learning style. I can't tailor the class to everyone's learning style. I do it to the average that I think, okay? And some of you, not a lot of you, some of you will fall off out of this, the style that I'm teaching based on. So that's a fair request. And you wanted me to adjust to your specific style, but maybe office hours are better for those. So show up in office hours, ask question over the email, Zoom outside of office hour. You don't have to necessarily come to office hours. We are almost at the end of the semester. We still have 3 more weeks to go, right? So if you didn't do it so far, do it now. Well, he is a graduate student, so I can ask him to work outside of his office hours, but I know Brett does. But I'm here to do that. So you can even check my calendar on Outlook and you see what time are available. And I am obligated to meet you on those times, and I will. I think most of you like the way that the topics are taught, so it kind of builds on top of each other. Again, I'm not following the book by the letter, so sometimes I change things. I think there were 1 or 2 that didn't like my style, didn't like anything in the class. They didn't want to be in the class. I'm sorry that happened, but I don't know if you didn't raise any question or ask me to change something. So if it's in your head and you never communicated with me, I can't read your mind. I try my best. So if you are here, you're hearing me, if you're not comfortable to be in the class, you can talk to SLDS and then they will find you a way not to be in the class. I don't want you to drag you to the class. I think being here is very useful. Okay. But it's your choice, it's your money, it's your understanding and learning. I can push you so far, right? But overall, I think everyone is kind of at the same wavelength of the class, and it's good. Then homework 5 is going to be a project, right? So it's a big question, basically, that covers everything you learned so far. So to give you a good idea of what problems in real life could be, and then how do we solve and go about it to design a controller. On Wednesday, I'm going to discuss about the plant, the system a little bit, because the DC motor has an electric part and mechanical part. The other comment was that most of you, I know you're trying your best, but when it comes to mechanical aspect of this, everyone like has a hard time, not everyone, again, most of you have hard time to understand the mechanical part. I think when we talk about diversity, that's a good point. I have a mechanical background, so I am the element of diversity in this department. Okay, apart from being woman, brown, from Iran. From my technical background, I'm also diverse, right? So this is an advantage because so far you have been always taught electrical stuff, right? Any system has mechanical part in it. So this is your chance to understand that part. One course is enough because you're gonna be expert in the electrical part, but you need to understand the mechanical aspect too, right? So I would say, take this disadvantage and make it advantage. When life gives you lemon, make lemonade, right? So, no, okay, just eat the lemon. But it's good because when you understand how mechanical system behave, you already know the electrical system, right? And then if you are interested in control, the next class you take, then you will have the example that have both of them in them. You can't eliminate mechanical system from this course. If you go take robotics, you'll see, you think there are so many electrical components in a robot. We barely talk about electric components. We just talk about mechanical parts, which basically is the equation of motion. Now, every system can have equation of motion, right? Electrical and mechanical. So I'm trying to teach you the basic with a different flavor. And I understand you are non-mechanical engineers, right? So I try to choose simpler question. Trust me, if this was in a mechanical department, question would be very different, and it should be. All right. And I tried to throw a few electrical, and then some of you complained why I use op amp. That's my best of electrical system. I'm not an electrical engineer, but I'm a control engineer. You can take advantage of that part. So I gave you electromechanical system for your homework. It's simple. And then I will talk about it on Wednesday to help you how to start creating your structure. All right. But this is a little bit different from your other homework. You have to actually come to my office and justify your design. So if you come to my office and ask you a question about a control that you designed, you cannot defend yourself, you will not get the 40 points of what you did in your report. Because this is an open-ended, the solution is on the internet. And I'm aware of that. But the goal is, if you understand, if you should, first of all, be doing it yourself, and you cannot get help from anyone, right? It's your project. If you hit a wall, you don't know what to do, you couldn't find either of us, like, let me just look what other people did, just get an idea. It's okay. Don't copy paste everything from the internet, please. You just want to get an idea. If you got an idea and you did yourself, so it means that you understood, right? So when you come to my office, I need to see that understanding. If I didn't see that understanding in any part, transfer function, system response, I don't know, root locus, any of those, you're not going to get points for that. All right. I'm not trying to scare you. It's just, even if I see that you understood, you couldn't put it in, I don't know, in mathematics, you might actually get some points because you could explain it. So think of it both ways. Now you have to schedule your interview. Schedule one section per person. Did you get my message that you scheduled two? Warren? No, Warren. Yeah. So it shows 2. So if you schedule more than one and then it's like, oh, I didn't want this, I'm gonna get another one, that is already scheduled for you. So you're taking someone else's time. All right. Now to do that, the easiest way is to go to your calendar. You can even do it now. If you want, you can do it later. It's better to read the question and see what it is, then it's schedule. So here this week, and then one of this time, click and you take it. But you have to, on your calendar, pick this class. So all the available time workshops. So some of you already did that. So 13, 14, 15, and 18. So the homework is released on 4th. It's going to be due on 14th, 10 days. Most of it, you already know what to do. The only thing that you need extra is today's lecture. Then after that, you can start just looking at it. All right. So based on your capabilities so far, you can, I think, go ahead and schedule. And I think those time will go soon because most of you probably want to schedule at the end. I don't know. These are all my availabilities. So I would say do this sooner than later. And if you go back to module, you can even see the project. If you have a question, you can ask me. I would not help you on the assignment, is a homework, right? But we can discuss about it like engineers, brainstorm. But I'm not going to tell you if this is correct or not correct. All right. So that would be homework 5, and you choose your interview date. The other comment was about final exam. Yes, we do have final exam. Adrian already asked in Discord, and I told him the date, and everybody probably see it. So this exam date is based on registrar, right? So if you go to their website, so it's Friday. What? I have to go back to Discord. Nobody knows? Great. Someone trying to say it, but I don't know. This? Oh. There you go. Friday, April 29, 4 to 5:45. So if you're SLDS, schedule. All right. There will be again cheat sheet, and I'll tell you everything after exam 2 is going to be in exam 3 or final exam. So it's not cumulative, it's just the remaining. So it's not comprehensive. All right. The reason being that I used to have final project and student would not study anything that was not in the final project. And I think the end of actually this course is a lot more important than beginning. So making an exam, so you would study. All right, trust me, it is good. It's good stuff. Good stuff is at the end. So any question on any of this logistic and stuff I talked before we go to our class? Everything clear? All right, sweet. So let's go back to, oh, I cannot minimize that. I can never learn. Going to share today's lecture. I forgot to upload it. I mean, I uploaded, I forgot to give you access to them. Sorry, I was very, very busy. I thought I did, and then I realized I didn't, but I did at 1. So those of you that print them, I apologize. All right, so I will introduce a different type of controller today. So you learn PID controllers, right? And in the exam, you should understand what PID controls are. So I'm kind of confident about the class. Now, so today we are gonna check what lead and lag compensator are. So compensators are also controllers. They compensate for something, and you'll see why. So if you hear controller or compensator, they are the same thing. It means that they're trying to change the behavior of your system. All right. They can be called different things. Now, we are moving from PID controller, all right? So we have, you remember pole zero placement that we discussed? That if you add a pole to a system, will change the behavior of a system. So lead and lag compensator are basically a pair of pole and zero. Now, the way they are arranged are defined there if they are lead control or lag controller. All right. So if you have a system, let's say this is G of S, this is your plant and everything. All right. It could be a feedback inside of it. I'm just showing you the whole system as GS. And let's say we are designing a controller for it. I'm going to say GC, G of controller. In a feedback, unity feedback loop, negative, positive, R, Y. Okay, so we want to know what is inside of GC for a lead controller. So we said it's a pair of pole and zero. Now I'm going to draw just the S domain for the controller only. Real axis. So if we place a zero, so it's pair of zero and pole, there's two situations. Well, there's three. If they're on top of each other, they cancel each other out, so there's no point. The zero could be closer to the imaginary line, then you can have the pole, right? And then the other one is backward. So if the zero is closer to the imaginary axis, is leading it, however you want to remember it, this would be the layout of your lead controller. Now, they don't have to be real pole zero, they can be conjugate pairs. Okay, but as long as the zero that you placed in the system, it didn't exist, it's a new zero you put, then you have to put a pole as well. These two pairs are going to be your lead controller. All right, now the transfer function for the G of C is going to be, well, we have a zero in the numerator, we have a pole in the denominator, right? We also can have a gain. Could be, you also might need to amplify this whole thing, right? So we can write the transfer function of the control as G of C, a K, which is your gain. If it was 1, still a gain, but it's 1, right? So it can be greater than 1. S plus Z, Z is the location of your zero, which is closer to your imaginary axis, and P is the location of pole. So this is the transfer function. If you look in your textbook or other textbook, you see that there's also like a formula based on alpha and tau. So alpha is the ratio of pole to zero, right? And since the pole is greater, it's farther. So pole to zero is going to be greater than 1, right? And your tau would be 1 over P. So if you have to decide where your pole and zero are going to be. So if you find them, and then if you create these two relationships, you can write the transfer function as K times 1 plus alpha tau S over alpha 1 plus tau S. So it looks like inside of a filter, right? So if you want to look at that way. Otherwise, you can just use the direct K times S plus C over S plus P. They are the same thing, just different notation. You might see either one on your textbook or questions. Now, doing that, we are changing the behavior of our system. Now, you remember root locus, right? So adding those two will change the shape of the root locus. So since root locus was trying to show you all the K values that if you design a controller K would land on the system, you're introducing two other, a pole and a zero, right? So now with those, you're going to see where the controllers are going to be. So usually what happens is that root locus will be gravitated toward the added pole and zero. So if some part of root locus was on a stable side, if you add a pole and zero lead controller, you can drag everything to the stable side. We will see that. We're going to draw and then we'll see that. All right. So this is one technique. This is lead controller. Now, I will explain what a lead controller does. So you can tell, oh, my system does such and such. So let's design a lead controller. But let's work on the layout first. Now, guess how does a lag controller look like on the S domain? So I'm gonna grab this guy, same system, right? This time, the pole and zero pair are switched. Now this time your pole is closer. When I say close, it doesn't have to be like really close. It could be here and here, right? So this is the lag control we're adding. We are putting our pole closer to the imaginary axis. Usually when we design lag controller, is usually everything is a lot closer to imaginary axis. So the numbers are very small. Now, if you have a pole so that pole, if it goes further closer to imaginary axis, is going to be like a pole at zero, right? What was the specification of a pole that is on the zero? On the zero of this here, center here, origin. So we are choosing a pole very close to the origin, and I put a zero close to it, right, on the left-hand side of it. So what do you expect to happen to our system when that pole is close to the origin? Okay, so 1 over S, that's what you mean? Okay, what is that? Like an integrator, right? When did we use integrator in our system? We had to use integrator when we had a steady state error, someone said, right? So if your system has a steady state error and you want to design a controller, you could design a PID controller. You could also design a lag controller. So in PID, the D part is kind of your zero, right? Here, so that's a different type of controller. Here you say, you have an option. I want to design a lag. I want to put a pole close to the origin, but not on top of the origin, not on the origin. I'm going to put a zero to the left side of it. This is the combination of a lag controller. All right, the different controller design. A PI would work, a lag controller would work too. All right. Then the transfer function is kind of the same thing, but the numbers are different, right? This time your P is smaller than your zero. So Z over P this time is going to be greater, right? Now, the cool thing about this method is that when I will introduce you to the control design app, you can move, you place a pair of zero and pole, you can move them, literally you can drag them, change their value, and observe the response of your system. So you don't know where they should be, you guess, you come up with an educated guess. And then by dragging and looking at the response, you can find a final value for them, or close to enough, because you're always going to have a requirement. So your system will meet your requirement. Example, where's my cheat sheet? A simple root locus. If you're designing a root locus and your transfer function looks like that, can you draw the root locus for me quickly? So this K is, you can find it from root locus and find a way that the system is stable. But do you remember how to draw the root locus for this? No. Let's do it together. So we are in S domain, right? We draw our poles and we don't have a zero, all the poles. How many zeros we have here? Nada. What happens to these two poles? Where do they find their zeros? Come on. Okay, right? So we know there will be asymptotes. You have to do all of those things, center of asymptote, the angle that the asymptote, all find all of those. But since we have seen this many, many times, we already know is going to look like, this one goes up. It doesn't matter. Then the system now. That's the one. We've done this. So this is like really close to like here. All right, remember that? We've done this before. Now, let's say that we have some requirement that we need to design a lead or lag controller. Now, if I design a lead controller for this, it means that I'm going to add a pair of 0 and pole. The 0 is closer to the imaginary axis. So it would look like so for this example, it's pretty simple. I chose this because it's simple. So I'm going to put my 0 here, and the pole has to be the left side. So the 0 is close. It doesn't have to be closer than all the other pole and 0 to imaginary axis. It just has to be closer than its own pole, because these two are lead controller. Since our system was stable, definitely this design of lead controller was not to increase the stability. However, there was other specification to be met. Now, the root locus will go from here to here, right? So it just gave us some extra Ks that we can put in the system. The system is still stable. Now, if I want to write the transfer function of this system, what's the transfer function of that controller? Hold on, you can't tell. So if this was -4 and -5. Now, what is GC? Someone can just yell. So yes, but you want to design them separately, right? Because we're just trying to show the, so the controller, the GC is this. This was your G, and this was K. Now, if you want, now this, so your K here is 1, right? There could have been another gain in your system. You're not going to delete that. You're going to still use that. The previous K didn't work for you. You still keep it, but the system is stable. You're adding another controller to it. So this whole thing now becomes your controller, and this is your system, right? So what you're trying to say, you're trying to multiply all by each other is fine, but again, separately, system, controller, and the gain that you had from before. If you take, you could be gain system. Now, if I design a lag controller for that, so if we look at the response of that system, you will use MATLAB, don't worry, I'm just going to show you. So the response of the system looked like this. So there was some steady state error in that system. Now, we know that we have to designing a lag control is better, because lag control is going to get rid of the steady state for us, because it has a pole close to the origin, right? So we will say, okay, if this was -1, this was -3, this time I'm going to put a pole and a 0 close to the origin, -0.1, -0.3. These pair are going to help the steady state error of the system. So let me draw the thing here. The root locus part of that, and the root locus part of this is going to be here. Now, if you look at the response changed. So this was a steady state error. This is with lag compensator. So adding those got rid of the steady state error. Now, you could say, I could design a PI controller, do it. That would have been fine. You could also design a lag controller. You could also design many other controllers. All right, so it's really dependent on which one you're more comfortable with. If there's any other requirement, what does this mean in physical system, all of this. All right, if it's a digital control, go for it. You don't have to do it as much as you need to. But you should be very comfortable using the MATLAB system toolbox. All right, so before we go to this MATLAB example, what I'm going to do is, if you have your laptop computer, go to MATLAB online. If not, you can just follow me. I'm going to stop that.
try to share my screen. Jeffrey, do you see the MATLAB page? Yes, okay. So build your favorite transfer function. Doesn't matter. I'm gonna say 1 divide by, no, let's divide. S squared plus 2 times S plus 1. Let's make it S plus 2 plus S 5S plus 3. So this puts the transfer function at, oh, it has to be 6, right? Yeah, that puts at 2 and 3. All right. So let's run this. Hold on. See, clear all. All right, let's clear it, run, and see what happens here. Oh, I'm just gonna see root locus because I did not call that one, figure 1. Okay, so this is the root locus, grid on. Run this as well. Okay, so grid on. So for root locus grid on, it will show you omega n and zeta. You've used that before, right, in the exam? So let's say if I wanted to see the step response, I need to create another figure, right? So let's say figure 2, if this works, because I didn't introduce figure 1, I messed this up. 1, this. We'll see. Let's plot that as well. Okay, keeps both of them. So here you have both of them. There's obviously steady state error because it was a step function, right? And then, well, both of them are on the left side. So this is a stable. We need to get rid of this steady state. So you could go by and design a PI controller, go to use the script, or go to Simulink, add your PI control here, right? Now, another tool that you can use to see both of these side by side instead of just going from one to another and manipulate it is to use this command, control system designer. Now, control system designer includes all the plots and all the analysis for your control. So you might not have it actually if you didn't, well, you installed control toolbox, right, before, so you should have it. If you run this and identify what is it that you want to see, the analysis, root locus, we can later do Bode plot. You can ask what I want to see, and then it shows you that plus the step response, and then you see your system. So if you run this, you can do that later. We are going to use it for that bigger example. This is just a simple system that we created. All right. So control system designer opens, and you can see those two side by side. Now, we said that all these values on the root locus are the system times K, right? You see these 2 pink points? These are graph points. Now look at the step response. It's changing, right? So what is happening? By moving this pink part, I'm saying this is the K values that will give you specific poles and zeros, right? So let's say you want to pick K of 10. What would be the step response? You're going to say K now is 200. What's the step response? So moving this up and down, increasing or decreasing the value of K, you can see the values are down below. Let me put this up here. So look down here. So damping natural frequency, current value of your pole and zeros. You can see that you're getting close to, like, then you have to do that. So we're trying to get rid of our steady state error. I'm increasing K constantly, is going up. Obviously, it's not getting, and the more I increase, the shape of that response is changing. I still have, so I'm increasing K by a lot. I still have a steady state, right? So at some point you say, okay, I need to design a controller that has a pole either on the origin or close to origin. So either PID route or lag compensator route. So adding something closer to origin. Now, the cool thing about this is if you, I keep saying cool thing, but if you keep here, right click, you can add a pole and zero. So you can say add a real pole, add a complex pole, add integrator for PI, right? We're not going to do that. We're just going to add real pole and zeros. So let's say that we're adding a real pole. I'm going to choose here, change the shape of the root locus and change the shape of the response, but I still need to add a zero, right? So add a real zero. So if I want it to be lag, it has to be here on the other side. So changing the shape now, I didn't choose it close to imaginary axis. So if I move this guy closer to imaginary axis and then pick this one closer to this. Okay, and then you can also change the gain of your controller. Let's say the gain is 3, but if I said 50, so here tells you where you put the pole 0, and you see that already we are close to getting our steady state. So you can basically play with this, move this around a little bit. You see that I get it close, is not changing, so I might need to increase the C value, or I need to design a lag controller, or I could even choose, so you could delete those and maybe add complex pole and zeros. That might actually help to have an imaginary part here, as long as it's close, right? So this is the part that you have to, so you're building the controller and adjusting the value. Now, if you would go with MATLAB script, what would you do if you didn't have this tool? GC is S plus some value over S plus some other value, and then create a vector, or just keep changing those, looking at the step response to get close enough or not. So it's possible through script, is a lot easier here. So the thing is, if you wanted to look at body plot, you could also bring body plot here, and then also look at the body plot. All right, we will go over those later. But when we talk about the frequency response, you'll see that we can have all 3 of them actually there. Yeah.
In industry, there's some practical difference that makes, say, a lag controller or a PI controller more favorable.
In industry, they use PID. So lead lag controller also has something with frequency. So if the frequency of your system was important for you, you could go about lag and lead. But for them, to make it to make it easier, they use PID. If you think about PID, is also a zero, a pole, and a K value, right? KP. But that you get some response from your system from the directly error. So it has a direct relation to error. Here it's just like placing a pole 0 to change the behavior of the system. Okay, so that'll be the difference. If you talk to people in industry, they will say, "Oh, PID control is good. Forget about it and that." So I'm teaching you different methods. It might work for you, it might, depend on your system, depend on what you're doing. The next thing we'll learn is using body plot to design something. So we would use this compensator when we're using the frequency response. So as electrical engineers, actually, you look at frequency response a lot more. So that might be more valid for your design. And as you saw, the shape of it looked like a filter, the other one with tau and alpha. So it has more meaning, perhaps, to your application. All right. Now, I'm going to open the other example and discuss that. But for that, you also need to have computer. So I'm going to go over it quick, like briefly, but my expectation is that eventually you will go home and run all of those. I have given all the values in the lecture, so hopefully it should not be a problem. So cleaning all of that, this example, run this, there's a G servo. And if you look at lecture slide 6, it tells you this is an electrohydraulic servo mechanism. And so it's a compensator, C, G servo is your plant. And you get a reference position and you're trying to control a ram position, all right? Well, do you want me to show that a slide or you're looking at the slide? You want me to show that slide? Show your hand, raise your hand if you want me to show that slide. Okay, I'm gonna listen to Wilson. Let's do that so you know what the system is. Here's a system. So compensator or controller, your system plant which you're loading, and then after we load that, we're going to open. So if you pay attention, our desired value is a position, right? Goes to a controller because it's trying to check the error. But then the value that goes to the plant is a voltage, right? The output of control has to be converted somewhere there. Either is in the controller inside the plant or something outside of the controller that does that conversion for us. The requirement for this design is the 2% settling time should be less than 0.05 seconds, and maximum overshoot is less than 5%. Now, if we do that, if we load it, okay, so this is the root locus. I'm not expecting you to draw that because there's so much going on, but now you know what does it mean. It means that if your poles are on this side, the system is going to be unstable. I'm going to prove it to you. So those lines are, if we, yeah, right that. Then as soon as we pass over to the left side, everything is becoming stable. So the system doesn't have a steady state error, right? If we look at the system properties, characteristics, we need a settling time, right? Settling time needed to be less than 0.05 seconds, and it is 33 seconds or something. No, a lot, like 30 seconds. Very, very slow. We need to make the system fast. There is no overshoot right now, but imagine you want to make the system fast, you're going to see oscillation. So you have to compensate for that. So there will be an overshoot. So it doesn't have to be 0, it can be less than 5%. Now, all we have to do is to add some poles and zeros as our compensator and see how the system will react. Okay? Any questions? Why are everybody so tired? I am tired, but why? Exam weeks again? Okay. I feel like, again, what I'm saying, it doesn't really matter because most of you are going to look at it later. So it's like, let's go. Okay, I'm going to let you go actually. So here, a lot of time by changing the compensator gain, you can see a lot of improvement in the system, meaning that just amplifying, make it go faster. It's like a KP, right? Just makes the system goes faster. Just try value 50. Why 50? I don't know. 50. Whoa. Okay, how about we don't change that? Whatever it was. What was it? Negative? No, it should not be a negative number. Here, back to 3. I just put a number. That was 2. Ooh, look at that, 0.72. I'm a genius. I have a good intuition. No, I have not. I just put a number. So just want to try, right? We do that. Now we need to add a pole and 0. So my plan would be for you to do the rest of this at home, because in the lecture, you place :0 imaginary. Design a lead lag controller. Here lead because there's no error to add a lag controller. Review that. I saw Wednesday class is reviewing this. All right. We talk about the homework and then go to frequency response. So I'm putting it on your shoulder. There's no class participation today. My expectation is to go over the slides from page 8. Just build whatever I said to get a sense of how to manipulate. Okay, and then take 10 minutes to rest before the next thing. All right. Okay, that's about it. Oh, I said goodbye. Let me pause.